continue the morning session and proceed to the last talk by Felipe Ángeles on local well-posedness for fractional Navier-Stokes equations. Please.
Thank you very much for the invitation. Well, the title of my talk is Local Well-Posedness for the Fractional Navier-Stokes Equations for Compressible Fluids. Okay. First, I want to talk about the motivation for the compressible model, for the compressible regularization, okay? And the story begins with the incompressible Navier-Stokes equations, okay? The incompressible Navier-Stokes equations is this system of equations, okay, with an initial condition, but the viscosity term is now given by a fractional Laplacian, where the fractional parameter is alpha. If alpha equals 1, we obtain the standard Navier-Stokes equations. Okay? The system of equations was introduced by Lyons, but with purely mathematical interest. He wanted to construct solutions to the Navier-Stokes equations by a vanishing viscosity method. So he introduces an artificial viscosity in the Navier-Stokes equations, and he realizes that if alpha is bigger than this quantity, now known as Lyon's limit or Lyon's exponent, then the global regularity problem for this equation has a positive solution. Okay, so this has a unique global solution for all times. Okay, so Lyon's example left us with an idea. It may be the case that the intensification of the dissipative terms implies a better control in the energy of the solution. Okay? This is just an idea, but it has motivated the variance hyper and hypodissipative of the incompressible Navier-Stokes equations. By this, I mean the following. Consider the generalized incompressible Navier-Stokes equations. Why generalized? Because now the viscosity is given by a Fourier multiplier with a symbol given a function of chi square. Chi square is the dissipativity produced by the Laplacian, the symbol of the Laplacian. Okay? And we refer to it as dissipation unit. We say that a model for the incompressible Navier-Stokes equations is hyperdissipative if it intensifies the growth of the dissipation unit. And it is hypodissipative if attenuates its growth. Okay? So in the case of the fractional models, if alpha is bigger than 1, we have a hyperdissipative model, and in the other case, we have a hypodissipative model. And let me tell you something important. These words hyper and hypodissipativity are not statements about the L2 decay of the solution. In fact, if you consider the fractional heat equation, okay, with a smooth enough initial condition, this equation has this decay. And in the hypodissipative case, it goes faster to 0 than the actual heat equation. Okay? So it is the case that in this example, the notions of hyperdissipativity and hypodissipativity are inverted to the thing that one is thinking. Okay? Well, now Lyon's example is hyperdissipative. Okay? Since alpha is bigger than d plus 2 over 4, d is always, in incompressible fluid dynamics, greater or equal than 2, with the exception of the case d equal to and alpha equals 1, okay? Which is the bidimensional dissipative case, and which is known to have global regularity since the works of Leray, okay? So there is an important question. Why is it that these cases preserve the regularity of the initial data, independently of the size of the initial data? This is the question of global regularity, okay? There is no answer to this question. There is only one attempt to answer to this question, which is called the supercriticality, okay? You have here the total energy associated to the incompressible Navier-Stokes equations in the fractional case. The equation is invariant under this scaling, and the energy of the rescaled solution satisfies this identity. And we call the equation critical if the energy is scaling invariant, that is, if alpha equals Lyon's limit. It is subcritical if it exceeds the limit okay? Because in that case, we know that this system of equations has a global regularity, okay? And it is supercritical in the other case. And the point of this scaling is that you should think of it as some kind of microscope that enhances the behavior at finer scales, okay? And it is telling us in the supercritical regime that we have more problems. It is harder to control the energy of the rescale solution when we move to finer and finer scales. And you can see it over here. If we have a universal constant for the total energy, in the supercritical case with lambda between 0 and 1, we do not have the same bound for the rescale solution. Okay? So this is a problem, right? So there are several examples, important examples, of hyper and hypodissipative cases. One was proposed by Tao with this symbol. He proves global regularity for the generalized Navier-Stokes equations with a fraction, a logarithmic fraction, in fact, of the fractional model with Lyon's exponent. Okay? This example is cooked up in such a way that it lies just below Lyon's limit and above the dissipation unit. So for this reason, this case is considered hyperdissipative. There are two regions of interest, the hyperdissipative one, below Lyon's limit and above the dissipation unit, and the hypodissipative. Okay? And we have very important results in these regimes, but the point is that the compressible Navier-Stokes equations appear just as another example of supercriticality, just as the incompressible Navier-Stokes equations do. Okay? These equations were proposed by Wang and Zhang in 2023. The difference is that now we have an equation for the mass density, the continuity equation, and this corresponds to a fractional regularization of an isentropic model. Okay? In this case, the thermodynamical pressure is assumed to be given by a power law. Wang and Zhang consider the Cauchy problem for this equation, for this system of equations, by assuming that the initial condition is sufficiently close to a constant equilibrium state. And they managed to show global regularity and optimal decay of the solution under the assumption that the fractional parameter is above 1/2, 1/2, and 1. Okay? This should look strange to you, because the question of global regularity is actually a question independently of the smallness of the initial condition. And by assuming this, that the solution is very close to an equilibrium state, you're actually still within the realm of smallness. So you should have global existence independently of the size of the fractional parameter. Okay? When one revises the paper, you can find out that this assumption is only playing the role of assuring the optimal decay of the solution. Okay? These equations they describe nothing in nature. Okay? They are only an example of supercriticality. In order for this to have a chance to model, to describe compressible fluid dynamics, this term would need to be the divergence of something, and it is not. Okay? So this is only an example of hypodissipativity and supercriticality. This is the point. Okay? Now, don't get me wrong, there are models in compressible fluid dynamics, or not necessarily compressible, in fluid dynamics, that by their own right have a fractional term. And this is the case for the quasi-geostrophic approximation in atmospheric sciences. Okay? Now, Wang and Zhang introduced this change of variables in order to transform the equations into this system of equations. This type of change of variables was introduced by Matsumura and Nishida for the compressible Navier-Stokes equations. The point of the change of variables is that it transformed the system into a quasi-linear system with symmetric coefficients. Okay? But the problem is that this change of variables only applies to the compressible Navier-Stokes equations. You cannot apply it to any other type of system in compressible fluid dynamics. It's a very particular property of the compressible Navier-Stokes equations. The standard in compressible fluid dynamics is first, I'm going to write the system in quasi-linear form, okay? Independently if the coefficients are symmetric or not. Then I'm going to look for a Friedrich symmetrizer, a smooth, symmetric, positive definite matrix function, okay, that symmetrizes the coefficients. Okay? Then if you follow this method, you will obtain a system of this kind in which the coefficient of the time derivative will be the Friedrich symmetrizer. Okay? Now, this is the way to proceed. Okay? In this case, I'm using general numbers here. All these coefficients are matrices, are smooth matrices of order n squared, okay? And A0, since this is the symmetrizer, it is symmetric and positive definite. The symmetrizability assumption on the first order symbol is important because it implies the hyperbolicity, which in turn implies that the model for the ideal fluid is well posed in L2 and Sobolev spaces. This is a requirement in compressible fluid dynamics. Okay? And this result was shown by Cayetani in the case of constant coefficients and Cano in the case of smooth coefficients depending on the space and the time. Okay? And by L2 well posedness, I mean this energy estimate. Nonetheless, when B equals 0, okay, when I have no viscosity of any kind, the hyperbolicity is not sufficient for the L2 well posedness. And there are several examples showing this. If I consider a symmetric hyperbolic parabolic system of this kind, okay, that in which the viscosity tensor satisfies the Legendre-Hadamard ellipticity condition, okay, which is telling me that the system is parabolic, then the assumption of symmetric symbol, of the symmetrizability of the first order symbol is not necessary. But this is not the type of systems that appear in compressible fluid dynamics. In compressible fluid dynamics, we only have at most a subblock of the viscosity tensor that satisfies the Legendre-Hadamard condition. And this is because we always have the equation for conservation of mass. The kernel of our viscosity tensor is always different from 0. Okay? Now, in this paper, I showed that if only a subblock of the viscosity tensor satisfies this condition of ellipticity, then the system is well posed in L2. It can be well posed in L2 independently if it satisfies the hyperbolicity condition. Okay? Now, from a mathematical point of view, this is interesting because the system may not be hyperbolic. It may be only partially parabolic, and still it can be well posed in L2. And I provided an example, or rather I discovered it, which corresponds to the Cataneo-Christoph system. Obviously, because its first orders, the first order part of the system is not hyperbolic, the result compromised the predictions done by the Cataneo-Christoph system. Okay? So this raises the question, what kind of assumptions on the matrix coefficients are needed in order for the Cauchy problem of the fractional compressible Navier-Stokes equations to be well posed? Okay? So let us consider the linearization. And this is jargon. I'm not linearizing around any type of state. This is jargon. I only mean that I'm going to take a given function in some Banach space that depends on time, and in particularly that belongs to an open convex set in Rn. And I'm going to assume that it's given, and I'm going to try to solve this equation. Okay? The energy estimates anyway are done at the level of linearization. So if we assume some type of ellipticity assumption on the tensority, on the viscosity tensor, like this one, for example, this condition is not enough to assure the well-posedness. contrary to the hyperbolic parabolic case. Okay, so I need, in fact, the assumption of the symmetric symbol. And the explanation of this is very simple. If we take the equation, we can assume for the moment that A0 is the identity and every coefficient in the equation is constant. And I take the inner product of this equation with the function u, then I will obtain this estimate. This is consequence of the coercivity of the ellipticity assumption, okay? And this is obtained by Schwarz inequality. Now, if alpha equals 1, if I have the Laplacian, I can estimate this term in the following way. I can use Cauchy-Schwarz inequality, and then I can use Cauchy's weighted inequality to isolate this term involving the first order derivative. If I take epsilon sufficiently small, I can take it on the left-hand side of the inequality and absorb it. But this cannot happen if I have alpha between 0 and 1, because this norm here involves only fractional derivatives. Okay? So I require another condition on the coefficients. If the coefficients are real, as it is the case in compressible fluid dynamics, the only way to control this term is by assuming that the coefficients are symmetric, because in this case, this term will go to 0. If you are dealing with any other kind of systems, for example, a Schrödinger system of equations in which the coefficients on the systems have complex values, you can have different types of conditions to get rid of this term. Okay? And I suggest you this paper over here by Chihara. So the conditions that I require for my system to have a chance to be well posed are the following. My functions have to be smooth. Okay? This condition is the one that I inherit from the symmetrizer. This condition over here is the one that assures me that the ideal fluid is well posed. And in compressible fluid dynamics, I always make a partition in the variables, okay? Because there's always two types of variables, the variables that are involved in the dissipativity processes and the ones that are involved in the conservation process. Okay, the hyperbolic and the parabolic variables. For example, in the compressible Navier-Stokes equations, U will be the density, the mass density, and V will be the velocity. Okay, and I'm gonna make the assumption that the viscosity tensor has kernel different than 0, and it has an ellipticity condition, but only for a subblock of it. Okay, so this is the standard structure for the equations for a compressible fluid. Now, in general, if you want to solve the linear equation, you have two paths to follow. Either you use an evolution semigroup approach, okay? But if you use that, you require an extra ingredient. Either you use a vanishing viscosity method or a decoupling assumption. Why? Because usually the semigroup approach involves, the theorems are very absolute in the sense that they are either for hyperbolic equations or for parabolic equations. So if I'm gonna apply an evolution semigroup approach to my equations, I need to assume that there is another viscosity tensor here with another ellipticity assumption, and I'm gonna put an epsilon in front of it. And then I'm gonna apply the theorems for evolution semigroup, and then I'm gonna let epsilon go to 0. Okay, this is the method that I followed in this paper. Or you can follow Kawashima's approach, in which he assumes that the interaction between the hyperbolic and parabolic variables are part of the nonlinear terms. So he disappears them from the linearization, okay? I don't like this method because it changes the linearization of the system, okay? That means if you are using this method, it means that for you the linearization part of the system is only a transition to eventually obtain the fixed point theorem. Okay? So in fact, that's the reason for which I developed this method over here. And the other method that you can use is the approximation of the linear system plus a compactness argument. And we can follow the second path. I'm going to explain to you how. First, we're going to introduce a regularization. We're going to introduce the operator, the cutoff operator, defined on L2, okay, which is a Fourier multiplier with a characteristic function of the ball of radius n. Since the Fourier transform of this function has compact support, the function is smooth. So this is a modification of the function u. Okay? Moreover, contrary to the modification of Friedrichs, this is not only a self-adjoint operator, but is a projection. Okay, so it's idempotent, and this plays a key role in obtaining the energy estimates. Okay, so if I'm in the case of Wang and Shang, and A0 is the identity matrix, my modification of the equation will be this one. Okay, so I modify all the terms involving derivatives, okay, and the zero order term, and then since I can apply the Bernstein inequalities to this operator, it is very easy to show that it is continuous from L to N to L to N. And then I can use an ODE approach in order to show the existence of a sequence of solutions to these approximations. Okay? What happens in the case in which A0 is not the identity matrix? We can still use the ODE lemma to show the existence of approximations. But this ODE lemma is very powerful to be used without care. You might be tempted to multiply by the left the system and then modify. If you apply the ODE lemma to this equation, yes, you will obtain an approximation, the UN. But you will never be capable of obtaining the energy estimate for UN. Why? Because the multiplication by the left spoiled the symmetrizability of the system. Okay? So you have to use a method a little more complicated, which is not really complicated, but for this system, it turned out to be a little different. Okay? I have to introduce a new change of variables. I'm going to introduce the variable b, and I'm going to, which is the multiplication by the square root of A0. Okay? Maybe this is the new split of the variables, and we multiply the equation after applying the change of variables by the left, by the inverse of the square root of A0. You will obtain this system of equations. Observe the first part of the system, the coefficients of the first order part of the system, if are similar to the original coefficients, which means that they are symmetric. The B bar, the coefficient involving the viscosity, it is symmetric, and still it is positive definite or semi-positive definite. Okay, and we have a new coefficient involved in the zero order term, which doesn't really matter the form of it. Okay, but we have a new term, which is the commutator of the fractional Laplacian. Okay, which is this one. If we apply the change of variables and then modify the equation with the cutoff operator, the remaining equation will be this one. This is the correct approach in order to construct the approximations. The problem now is that we have here the commutator estimate for the fractional Laplacian. And the problem is that this term is exhausting the regularity of Bn, just as these other terms are doing. All the differential terms are exhausting the regularity of the equation, of the solution, right? The difference is that when I'm at the moment of obtaining the energy estimate, this will go to zero as consequence of the symmetrizability assumption, and this will be coercive. This will not have any of those properties. It is only exhausting the regularity of Bn. So in order to obtain a proper energy estimate for this equation, we need to have a commutator estimate for the fractional Laplacian. Okay? If this theorem over here is a typical commutator estimate that you can see that it applies for PDEs in general. It is the commutator estimate for the operator for the modification of Friedrichs. Okay? The point of a good enough commutator estimate is that you gain 1 degree of regularity by commutation. This is the point, right? So I'm gonna compute the HM norm of this commutator, but I am only controlling it with a norm with an HM minus 1 norm. Okay? Now, in this paper, Lee obtains a commutator estimate for the fractional Laplacian that have this form in LP, in L2, for example. And you can see this is a good enough commutator estimate because it is not exhausting all the regularity of the G function. Okay? This is a variant of the Kato-Ponce inequality, which was originally derived for this operator. To this day, I haven't found a good commutator estimate for my case because I need a commutator estimate for the HS norm with an S sufficiently large, for example, this one. But it doesn't really matter. We can use this result. This is a very good result, and we can construct the commutator estimate for the HS norm by means of the Bonis decomposition and the Littlewood-Paley theory. Okay? In order to do this, we need some ingredients. First, we need a dyadic partition of unity. I need to show the existence of 2 smooth functions radially symmetric, okay? One with support in a ball and one with support in an annulus. And they are a partition of unity. They satisfy these identities, okay? These other statements in the theorem imply the quasi-orthogonality of the dyadic blocks, and these statements over here are very useful when trying to characterize the Sobolev spaces or Besov spaces in terms of the dyadic blocks. Okay? Let me use this notation. Theta d of f, it is a Fourier multiplier with symbol theta, a smooth function with compact support. So we're going to define the non-homogeneous dyadic blocks and the non-homogeneous cutoff operators by these formulas. They are Fourier multipliers. But the point is that the Fourier transform of these blocks have support in a ball and support in an annulus. Okay? And we define also the cutoff operators in this way. And the point is that if I have a function, a tempered distribution, then its limit when j goes to infinity equals of the cutoff operators equals u. That is, in S prime, in the space of tempered distributions, the identity can be decomposed in this manner. Okay, so this is the Littlewood-Paley decomposition. Okay, now Bonis decomposition, on the other hand, is the following. If I have 2 tempered distributions and I write each of them by its Littlewood-Paley decomposition, I'm gonna take the product of these distributions as formally the product of the series. Okay? And we can decompose this product in this way. Okay? This product involves all the functions, all the dyadic blocks with Fourier transform of comparable sizes in terms of the support. Okay? And this sum can also be decomposed. One of the terms of this sum can be written in this way. Okay? Tu of b, which is the paraproduct of u and b. And the residue term corresponds to this sum over here. Bonis decomposition tells us that the product of ub can be written as the paraproduct between u and b and the paraproduct between b and u plus the residue. Okay? And the idea is if I have good enough estimates for each of these terms, then I can define in sufficiently smooth way the product of U and B. Okay, so this is the idea that I applied to the commutator estimates for the fractional Laplacian. I wrote each of these products as the corresponding paraproducts, and I discovered that the commutator estimate can be written in this way. Okay, observe that the sum of each sum contains commutator estimates of the fractional Laplacian. Okay, then we're going to use a lemma to characterize Sobolev spaces in terms of the dyadic blocks. If I have functions whose Fourier transform is compactly supported in an annulus times 2j, okay, which is the case of these commutator estimates, is simple to show it, okay? Then, and I have that this sequence of numbers is L2 summable, then the sum, in this case, it will be this one. This sum will belong to the space HS, and the HS norm, in fact, it is equivalent to this one. Okay? And what is the point here is that I only need to obtain good enough estimates for this sequence, and this sequence only involves the L2 norm. So I can apply the L2 case of the Kato-Ponce inequality. Okay? So let me show you how to obtain the estimate for this term over here. Since this is a commutator estimate for the fractional Laplacian, I'm going to multiply it to this factor, okay? And I'm going to use the fact that the cutoff operators are continuous on LP, independently of J, okay? So this can be bound, this has an upper bound, which is the derivative of f in L infinity. And this term over here is summable in L2. And in fact, it can be bounded by these quantities. It depends on the fractional parameter. Also, this term over here is summable. In fact, it is controlled by the L infinity norm of J, okay? And in fact, in order to obtain this inequality, you have to use an embedding theorem for the subspaces. And this inequality over here is the Sobolev embedding, because I am assuming, as previously wrote, that S is sufficiently large, okay? Now, in this case, we can obtain this commutator estimate for the fractional Laplacian. And observe, I am not gaining 1 degree of regularity. I am only gaining an alpha degree of regularity. Okay, so this is good enough because in this case, G, the function G is representing the velocity. And this is the type of norm that I can control for the velocity in the compressible Navier-Stokes equations. Now, if we have this commutator estimate, I can obtain the energy estimate in a proper manner, okay, without any other problem, okay, for some A in L1 that depends on the coefficients of the equation. From here forward, the local existence of the Navier-Stokes equations with a fractional regularization, it is standard, okay? For me, the more complicated part of it was the analysis of the linear problem because it had the commutator estimate for the fractional Laplacian. So that's it, and thank you again for the invitation, and congratulations to Professor Vilker for his birthday. Thank you.
Yeah, thank you very much for this very interesting presentation. We have lots of time for questions. Yes, please.
I didn't understand why when you multiply by A0 inverse, you spoil the symmetrization. A0 is a Friedrich symmetrizer or not? Or is just
A0, yes. it can be the Friedrich symmetrizer, but the inverse of the Friedrich symmetrizer.
Okay.
Yeah, even if it's a diagonal function, it spoils the symmetrizability of the first
Okay,
order part.
okay.
Yeah.
Thank you.
Other questions or remarks? Let me ask about this projection, the EN that you studied. I mean, how rapid is the growth of the energy in your solution if you remove the N, if you let N tend to infinity? Is the energy transported very quickly into modes of higher N?
Well, for the solution of the system of equation, no, that's not true because we have an energy estimate, right? So we can bound the energy independently of N. So that's the point of, in fact, yeah.
Thank you, very good. So, Søren.
Thank you for the talk. Can you maybe go back to the Cato-Ponce inequality?
Yep.
So, how general is your approach to generalize this? I mean, would this somehow give kind of any kind of natural generalization of the inequality that you would want, or are there still some cases left open?
No, this is a very particular case because my assumptions are, in fact, these ones over here for the functions involved in the commutator. So this is a very particular commutator estimate. I found different types of commutator estimates involving, for example, BMO norms. It may be that those are more general, but I only tried to solve my problem in this case, not really to generalize the commutation, the estimate of Cato-Ponce.
But your approach seems to be sort of a very robust approach that should give, well, maybe not the most general, but very, very general versions of the inequality.
I think my approach is, it is general, yes, because with Littlewood-Paley theory and Bonni's decomposition, you can prove a lot of inequalities in a very simple and short way, okay? However, the key part is the Cato-Ponce inequality, definitely. I mean, I think without it, my approach would have not worked. So, no, I have to give it to the Cato-Ponce inequality. That's the key part of my argument. The using Littlewood-Paley theory is in this case it would be standard. Yeah.
So, if there are no further questions, Miguel, please.
I mean, this approach that you have with the fractional Laplacian, that has a very nice, I mean, the presentation is very nice, and the method, as someone says, it looks robust in some parts. So what do you learn from this to solve the physical problem later? So I guess you have the intention to solve these physical problems later. Do you learn something from the methods that you developed in this work? Okay.
Do I learn something? Yes. Well, in most cases, I thought that the local, from the whole part of my time working with this problem, I thought that the local existence would be mostly standard. But the appearance of the commutator estimate for the fractional Laplacian is, to my knowledge, completely new. Okay, and that's because a lot of systems, for example, in the incompressible Navier-Stokes equations, a lot of systems do not have, or in fact, they assume that A0 is 1. is the identity matrix. So they don't have to deal with this term over here. But most of the terms, either using an ODE approach or using evolution semigroup approach of Cato, they always assume that A0 is the identity matrix. So I think that my analysis is more general in that sense. That, right? Yeah.
William, please.
Yes, this is very interesting to me because I've been trying to work with this little Palewood theory, so I hope you can teach me while I'm here in Mexico. But did it depend at all on putting your equation into something like ansatz of sorts to get this decomposition to converge, or did you take the linear case and then kind of do this Littlewood-Paley bony pair product on the perturbation? Or if you could comment a little bit on, I know is the content of your talk as well, but just this aspect of whether it's important to put your equation into a certain ansatz first or not.
But what do you mean by an ansatz? So for example, like what?
Well, and when I read about this, there's some instances where you basically create so an ansatz, I guess, is like a kind of a cutout or like a mold for what you're gonna have the equation look like, and then you sort of plug that into your equation and you see what comes out. So in the case of this pair-controlled calculus, which uses the Littlewood-Paley extensively, they first solve a differential equation driven by the potential, and then they use that as kind of a basis for their ansatz form. But it's also possible that this is not a good question for this forum.
Well, in this case, for me, the Littlewood-Paley theory was only a tool for dealing with the commutator estimate. I don't really use it in any other case of the analysis of the equation, either on the local or the global existence. No, it was only a tool that I had at my hand in order to try to obtain the commutator estimates. In fact, it was the one that worked because I tried different other ways to obtain the commutator estimate. But there are other equations in which the Bonis decomposition and the paraproduct is rather involved, but I would not say that this is the case. It was only a tool for me to obtain the commutator estimate. In this case.
Oh, that's very helpful, in fact. Thank you.
Okay, are there further questions? That does not seem to be the case, so let's thank Felipe again for this very nice talk.